So we have Matt Phillips, DSP and software engineer at Trident Audio. And Matt is going to be talking to us about a brief introduction to nonlinear audio DSP, which sounds really, really interesting. So I'm really looking forward to that. Over to you, Matt.
Okay, thank you so much. I'm going to share my screen. Okay, so really excited to be here. It's pretty excited when Josh said he wanted me to come and give a talk. And he, I like a challenge. And so when he said, "Can you talk about nonlinear DSP in 30 minutes?" I thought, sure, let's give it a whirl. There's a lot of information here. Those of you who have worked with nonlinear DSP before, you might be a little disappointed. It's probably not as in-depth as you might be used to. And those who've never worked with nonlinear audio DSP before, it may be a little complex in part. So I've tried to keep it pretty high level. But the purpose here really is to share some of the techniques that I've used in plugin development and really introduce the topic of nonlinear DSP and show you some of the tools that are available. So just a little bit about me. I've been working in the audio industry for over 15 years now. I've worked in fields of acoustical engineering, real-time DSP, hardware DSP design, software engineering. And this year at NAMM 2020, I released my first commercial plugins with Trident Audio. And had some nice reviews in the magazines that I've got on show there. So currently, I'm working on more plugins and some other exciting projects that will appear over time. So, just a quick overview of what we're going to be covering today. We're going to look at the term nonlinear systems, nonlinear DSP, and kind of cover what it actually means and what it means for us in audio world. A little section on nonlinear being a new buzzword in marketing and plugins, and just dispelling a few myths there. I'm going to talk about how to approach nonlinear audio problems. And then we're going to jump into a demonstration. I'll be doing I'll be running a MATLAB session live because it's more exciting when things don't work. But we'll be looking at how you can use something called FuzzyLogic to work with nonlinear problems. And then wrapping up at the end with just some guidance on how you can get started and some resources that are available to you. So we'll start with just a definition of what we mean when we say nonlinear. And at a system level, a system is nonlinear when the change in output is not proportional to the change in input. So the opposite to a linear system. And just to dive into that a little further, so unlike linear systems, nonlinear problems cannot be solved through what's called the superposition principle, which we'll go into a little bit more. So main thing to keep in mind there is the change in output not being proportional to the change in input. And when I say the superposition principle, what we mean there is for all linear systems, the net response caused by two or more stimuli is the sum of responses resulting from each individual stimulus, which is a little bit wordy, but what essentially that's saying is in a linear system, if input A is producing response X and input B is producing response Y, then A plus B produces response X plus Y. And that's how you can look at linear systems, and that will always be the case. That is not the case with a nonlinear system, which obviously raises some complications and extra work that we need to do in order to work with those kinds of systems. So in audio land, examples of components or systems that exhibit what I call well-known nonlinear behavior that we might all be familiar with as programmers and audio engineers. So things like tubes or valves, depending on where you're from in the world, transformers, magnetic tape effects, mechanical reverberation. So all these systems, these audio models based on these kind of systems are are kind of famous for their nonlinear behavior. So they're very difficult to approach them as a linear system because there are so many variables and parameters that aren't proportional. And in fact, something to keep in mind is that when we're modeling something, when we're working with something, any analog audio circuit exhibits degrees of nonlinear behavior. Some are, let's say, more nonlinear than others, but really any kind of analog electrical design is going to exhibit degrees of nonlinear behavior. And it's just a case of us choosing how we approach that, the scope of the project. So in DSP, linear implementations are often used to approximate nonlinear behavior, which is a completely valid way of approaching a problem. But in some cases, a linear representation is not an adequate solution for what we're trying to do. And the classic example, the example that I run into developing plugins, is that the sonic character of a vintage analog audio piece of hardware, for example, is often a result of its inherent nonlinearity. So if you try to represent that system using linear methods, then you're in fact glancing over some of the inherent characteristics and quality of that piece of gear. Just while we're kind of talking about plugins and nonlinear and audio DSP, nonlinear has become a kind of a buzzword in the audio software market. I'd say particularly regarding plugins, due to a combination of just marketing terms and just general information as it's spread around as people try to understand what nonlinear means. I've got a great example here from which I grabbed in December of 2019 from I call it an infamous gear discussion platform, make of that what you will, where someone had quite innocently said regarding a commercial plugin, love this plugin, it sounds sick as, will definitely end up buying when a nonlinear version comes out. And to my knowledge, there was, well, there was no penned nonlinear version of this specific thing, and it may already be nonlinear. But during discussions, people kind of say, well, if it's not nonlinear, then it's not going to sound as good as a linear design. So there's a little bit of misinformation out there. But the main thing really to keep in mind is that nonlinear signal processing is used to address complex problems that cannot be approximated by linear methods or cannot be linearized in an acceptable way. So nonlinear signal processing is by no means a must-have for every audio application. So if you can solve a problem through linear methods and it sounds great and you've achieved what you want to, that's completely valid. And in fact, nonlinear is really something that you delve into for specific problems. And modeling vintage or analog gear is one of those instances. But just something I wanted to throw out there, and certainly you see references to nonlinear more and more in forums and marketing and chat rooms and that kind of thing. So regarding approaching nonlinear audio problems, and for example, we're going to use modeling an existing hardware device. These are the steps that I personally take when approaching a problem like this. It's not necessarily the way that these problems have to be approached. I'm just sharing with you my approach and how I do things, and hopefully that might give you some ideas or just give you an insight into how I tackle these particular problems. And when I have a new piece of audio gear, particularly if it's vintage audio gear with pedigree and a well-established piece of equipment, the temptation is always to rush in and start looking at schematics and start running signals through it, taking measurements, however you choose to do that. What I always like to do is take a step back and spend a lot of time using the device without thinking about how I'm going to approach it, how I'm going to model it. Just use the device, learn about the device, and research the history of the device. Find out why people like it, what they like about it, what they don't like about it. And really important, talk to expert users of the device, because they will be able to give you some invaluable input onto what makes this particular piece of equipment worthwhile as a project. When you've done all this, then you're ready to define the scope of the project. And when I say define the scope of the project, what I'm referring to is looking to see what you actually want to model from that particular device. What are the characteristics that you like? Is it going to be suitable for a digital audio workstation environment? Is this going to fit in with a modern digital workflow? You may not want to model every nuance of a complex system. You may want to take parts of it. So this is really kind of, in my opinion, an invaluable step in looking at complex devices and how to approach them. Once you've done that, what I tend to do is then I will study the schematics, and I'll have a look and see what's going on at a component level, see how things are put together, how chains are formed, what types of components are being used, what's the heritage of those individual components, what's the history there, is everything working correctly? If you have your schematic, you can tell whether or not things should be functioning in a specific way. Schematics aren't always available, but they are obviously an invaluable tool if you do have them. And then we get to move on to our nonlinear approaches. Then what you'll need to do, or what I do, is gather the tools that you're going to use to identify your system. And when I say identify the system, because you're dealing with a nonlinear device where your output's not proportional to the input, you need to find out what's going on, what's it doing, how is it responding to signals, what kind of signals are causing these characteristics to happen, how can I work with that? So system identification is a field of engineering in itself, and is with a system like this, sometimes you'll hear people refer to it as black box or gray box. It's a way to start building information, start building a data set on how your device is functioning. So some common tools that can be used to do that. MATLAB, for example, they have a system identification toolbox. And there are other toolboxes that we'll be looking at shortly to kind of go into that in a little more detail. Methodology like NARMAX, nonlinear autoregressive moving average model with exigent. You say it's a mouthful, but NARMAX is the terminology or the abbreviation. Neural networks. So you'll hear a lot of reference to machine learning, AI, that kind of thing. Neural networks can be used to identify your system, to work with your system, and to build models of your system. And then something that we're going to be looking at today is FuzzyLogic. And I'm going to be running a little demonstration on how you can use FuzzyLogic with nonlinear systems to solve a relatively simple problem. So these are all methodologies I've used personally in plugin development, software development. We don't have time to go through all of them, but be aware that they are out there, and further reading on these is highly recommended. But looking at FuzzyLogic in particular, that's what we're going to be looking at today in terms of working with a nonlinear system. So FuzzyLogic is a way to map an input space to an output space, essentially. And the great thing about FuzzyLogic is it's intuitive methodology with minimal mathematical complexity. There is complexity there when you're using FuzzyLogic, when you're implementing it. It is very intuitive, and you're not going to be necessarily bombarded with mathematics and all that kind of stuff. It's a very logical approach to learning about a system and mapping input to output. It's quick, it's powerful for handling nonlinearity. It's scalable. You can make the systems as complex as you need to, but in essence, it's a fairly simple tool set to work with. And you can train certain systems that you make with FuzzyLogic methodology with data sets, large data sets. You have a lot of control over what you're doing. So it's a really great scalable system, and I would recommend that if you're unfamiliar with FuzzyLogic, or if you're interested in how you can use it to identify systems and solve problems, then it's something that's definitely worth reading up on. And I'll share a link to some good useful text at the end. So I'm not going to spend a lot of time going through the finer details of FuzzyLogic and what it is. We'll see through a working demo how it kind of works, or what it's doing to solve problems. But essentially, it's based upon the concept of precision versus significance. And this is my favorite FuzzyLogic kind of visual. So you'll see precision on the left-hand side and significance on the right-hand side. So you have a complex system. This example, someone's saying a 1,500 kilogram mass is approaching your head at 45.3 meters per second. That's the precise definition of what's going on. But the significance in the real world is, of course, look out, because it's going to land on your head. So what you're doing is you're really taking that precise, complex system and pulling from it the data that you need, the data that you really significant data that you need to address a problem or solve a problem. So I'm going to jump into a MATLAB demonstration. We're going to be looking at a specific problem in audio, which is noise cancellation. The reason I picked that, it's a nice visual way to show FuzzyLogic in action and to show how nonlinearity can be processed and how we can work with it and the tools that are available to do so. So I'm going to jump into MATLAB and we'll talk through each step as I run through it. So here's my MATLAB environment. For those of you who aren't familiar with MATLAB, it is a incredibly powerful program system that lots of engineers use, particularly with the work that I do. I rely heavily on MATLAB and the toolboxes that they have within them. This particular version of MATLAB that I'm running, if you're interested, is the 2020 release 5 edition. And I have some toolboxes that I'll be referring to within these demos that, and I'll give you information on those. But if you're not familiar with it, just kind of follow through what the process here. We're not going to look at the syntax of the code too much. It's really just jumping through a few steps just to give you a visual idea of what's happening and how you can use toolboxes like FuzzyLogic. So with our noise cancellation problem, we're going to set up a few parameters before we begin. And step one, we're going to generate an information signal. So the information signal is the important, significant information that we're looking to obtain from our eventual noisy signal. So I'm just going to run through each section at a time, and we'll run through it and gather data as we go. So what we're doing here is we're producing a simple signal here. So this is just a sine function with an exponent. We can see there's the sine wave there, and it's reducing in amplitude over time. So this is the signal that we're going to be interested in. Now, for the purposes of this exercise, we've created this signal, but in the real world, we wouldn't know what this signal is. This is the signal we're interested in, but we can't yet see it. So we're just setting up some parameters. So here's our information signal. This is what we want to hopefully end up with at the end. And of course, because we're in the real world, we're going to we're going to need some background noise. So there's always noise involved when working with signals. And so in this case, we're going to generate some random noise for the duration of the signal that we have here. So if we run this section, okay, so we have our now lovely looking random noise signal. So what's going to be happening is we have our information signal, we have our noise source. Now, rather than just having noise with a signal in there as well and trying to pull it out, what's most likely going to happen is that you are going to have what I call here an interference profile, where your information signal is going to be picking up noise, if you like, in a nonlinear way. So it's not just a case of having that noise overlaid on the signal. There's going to be some kind of nonlinear relationship between that background noise and the signal that you're intending to work with. So we're going to use a nonlinear equation here. And this is I don't want to say simple, but it's a nonlinear equation that will generate a noise profile for us. So if we run this section here, don't worry too much about the mathematics, but all we're doing is we're just plotting this function on a graph to have a look and see what it looks like. So if we run this section now, okay, so we should have our lovely nonlinear interference profile. So as you can see, through glancing immediately, you can tell not just by the form of the equation, but now through a surface plot, we can see that we have a nonlinear profile here. And this is the profile that we're going to be applying to our signals that we're interested in working with. So we're going to call our interference signal, which is a function of that nonlinearity and the random noise signal we created earlier. I'll run this section here. Okay, so we have our original noise source, which I've called N1. And underneath we have our interference signal, which is now that noise or that nonlinear equation, which we've run our noise signal through in order to produce this interference signal N2. And what we're going to end up with is what I'm going to call a measured signal, which is the sum of our information signal, that sine wave that we plotted at the beginning, and the interference signal, which now has our nonlinear component. So when we plot this section, this is what we end up with. So in the real world, we would have had two things available to us. We would have had we assume that we could have measured our background noise signal, our random noise signal, and we would have been able to measure this. Now this is our original information signal with that horrible nonlinear noise profile in place as well. So you can kind of see by looking at it, you can kind of see some peaks here where it kind of follows the original exponential sine wave. But when we get past really time t of 1.5, it's very hard to make out any kind of sinusoidal wave there or any kind of value that we'd be interested in. So this is where we can use the FuzzyLogic tool set within MATLAB to work with that data and to calculate or to estimate our original information signal. And we're going to use something called ANFIS, which is Adaptive Neurofuzzy Inference System. We're not going to delve into how that works or the mathematics behind it. We'll keep it very, very simple. But what we're going to do is we're going to feed in our original noise signal, our measured noise signal, with our measured information signal. And we're going to try to calculate that nonlinear relationship between the two with an aim to pull out a clean set of data. So the first thing we're going to do, step number 6, we're going to define our training data, which is our noise signal, our measured signal, and we need a delayed version of our noise signal to run through the blocks. So we'll just run this section. That's done. We'll move on to our next section. We're generating that inference system object. So we're setting some parameters here, some options through the genfis command in order to create our input inference system block. So if we run this section now, you can't see much happening in the background, but with MATLAB, we don't have it in a particularly verbose mode right now. But these things are happening in the background as we get towards our goal. Now what we're going to do is tune the inference system object using the data options that we've just defined. So I'll run this section. You see now we have some data coming back from MATLAB where it's specifying the number of nodes, number of linear parameters, nonlinear parameters, fuzzy rules. Don't worry too much about that. What we're doing here again is to get a visual representation of what it's doing. And you see it's reached an acceptable degree of training on the 10th step. Now we're going to evaluate the model that we've just trained. And what we can do now is we can plot the actual value of N2, which was our background noise, and that nonlinear component that we defined earlier. Plot those together so we can see the actual against the estimated. So when we run this section, you'll see at first glance, it's kind of difficult. They just look like two very noisy signals, but you will see some similarities between the two. So on the top, we have that actual N2 noise profile, noise signal that we generated, and underneath is the estimated N2. So this is what the FuzzyLogic, the inference system block, has calculated or estimated that the nonlinear relationship will be. And that's much easier to see when we go to our final step, which is plotting the original data signal, the one that we defined, the sine wave, against what our FuzzyLogic system has estimated to be the case. So when we run this section, okay, so we have two plots here. It may not be very clear to see, but in red is our original sine signal with the exponent. And overlaid in blue is the measured signal that our FuzzyLogic toolbox has taken from that very noisy data set that we had. That's what it's calculated. Now you'll see there are some kind of anomalies on some of the peaks here, and a couple anomalies on the bottom here. This is just from one round of training, so a very, very quick training round. We haven't tuned our parameters, we haven't tweaked our parameters, but we've got a pretty good representation of signal from our noisy measured signal just through using some tools that are readily available in the FuzzyLogic toolbox within MATLAB. So jump back to the slides now. So again, here's a summary of what we just did. It's sometimes a little bit difficult to follow any kind of MATLAB demonstration. But on the left-hand side here, we have our noise signals. This is our background noise signal that we can assume we would be able to measure as part of a noise cancellation system. In the middle, we have our measured signal, which was the signal that the information signal that we measured with that nonlinear component of noise signal embedded into it, if you like. And then the third step on the right-hand side is what I call the recovered signal. And that's the signal that our toolbox, our inference system methods have allowed us to derive. So you're probably thinking, that's great. How do I model my vintage EQ? After all, you've said in a nonlinear way. Well, there are starting points that I would recommend in tackling any kind of nonlinear system. If you've been able to follow any of what I've just done, you'll realize that there are that MATLAB, for example, shows there are a lot of potential avenues that you can start to explore in order to tackle your nonlinear problems. So specifically referring to MATLAB, the toolboxes that I use on a daily basis when I develop plugins are the signal processing toolbox, the audio system toolbox, the system identification toolbox, and the FuzzyLogic toolbox. I have some others, but these are the toolboxes that I rely on a day-to-day basis. And one of the most important add-ons for me is what's called MATLAB Coder. So when you're doing your R&D work in MATLAB and you're coming up with solutions to problems, you have your solutions from FuzzyLogic or neural networks or system identification, what you of course want to be able to do is take those into C++ and use in your juice projects, for example. A MATLAB Coder allows you to do that. and in combination with the audio system toolbox, you can actually generate juice projects. So you can generate a juicer file, which has all of your source, which will, in theory, build on first run when you open it in producer and then your IDE of choice. So MATLAB Coder, very, very powerful tool. The MATLAB Coder does require you to have a professional license of MATLAB, which can be expensive, but if you're a new business or you're starting out a new venture, it's always worth contacting MathWorks because they can quite often do some, make some allowances for you, set you up some demos, and identify a price point for you. The other toolboxes can be accessed using the home version of MATLAB. You're not allowed to produce anything commercial with it, or you shouldn't produce anything commercial with the home version. But if you want to try them out as demos and for your own personal projects, then the home version of MATLAB is affordable, and these toolboxes are available to you as well. Now, if you don't want to use MATLAB, there are some alternatives. So Octave is is similar to MATLAB. It's cross-compatible. It's through GNU, so it's open source. You can use it. You don't have to pay any royalties if you're using it for your projects. And largely speaking, cross-compatible with MATLAB. So it's designed so the syntax is somewhat interchangeable. I've worked with people who use Octave over MATLAB. They prefer the environment, so that's definitely something to check out. Another one is Scilab. It's a little different than MATLAB in terms of syntax, but is again a powerful tool if you do want to look into that one, and again, free to use. I quite often get asked what books whether I recommend for starting to work with nonlinear projects and audio DSP and engineering. This is a great one. FuzzyLogic with Engineering Applications by Timothy J. Ross. Really, really useful, has some great examples of nonlinear problems in there and how to solve them with FuzzyLogic. And then there is Nonlinear Programming. And a word of warning on this book, it is, I have my copy here, it's not for the faint-hearted. It's a very vast book. There's a lot of, you probably can't see, but there's a lot of very, very in-depth nonlinear mathematics there. So it's not for the faint of heart, but it is a really great resource when you come to working with, you start working with your really, really complex systems and design. So it's a useful resource to have on hand. And that's really all I have. Feel free, obviously there'll be a Q&A. Feel free to reach out to me personally if you have any questions you don't want to ask now, or you want any more information about any of this, matt@phillipsaudiodesigns.com. But I will hand back now. Thank you all very much for staying with that, and hopefully it made some sense, and hopefully it gave you some ideas on how you can start working with nonlinear audio and the tools that are potentially available to you.
Thank you very much, Matt, for your talk. Thank you very much, Matt, for your talk. Can you hear me now? I was muted. Great. So we have a couple questions, and there are some of them are around kind of the same subject area. So do you happen to know if there's any sort of C libraries for training and running these type of models?
That's a good question. I haven't used any specific C libraries for running and training these models. I rely very heavily on MATLAB and those blocks in conjunction with MATLAB Coder. So I'm generating C++ and C from the C libraries from the work that I do within MATLAB. I'm sure there probably are some great resources. In fact, it might be worth checking out the FuzzyLogic book that I recommended. I think I do recall some reference in there. If you can, I always suggest that people start with MATLAB, even if you're just running the free demo for a little while to get your kind of head around the toolboxes and how it works. If you don't want to make that leap and purchase a license, then Octave is a great way to move forward. MATLAB documentation is very useful. So you can kind of derive in a lot of times what you want to do from documentation that's already online, from MATLAB documentation, etc. It's a great question though. I would recommend checking out the FuzzyLogic book that I referenced.
Great. And another question was if there were any sort of, if you knew of any sort of Python or Octave equivalents of the FuzzyLogic toolbox. You happen to know
So
any?
the individual toolboxes within MATLAB, they don't always translate directly into Octave for obvious reasons. They're commercial products. But there are, Octave has a really active community. So if you're looking for specific, for example, neural network system identification or FuzzyLogic routines, functions, then jump into the forums on Octave, and people will quite often share their solutions. It's a very friendly community. So I would, although offhand, I don't know of any particular project names for any of the toolboxes I directly use in MATLAB. It wouldn't be surprising if there are already solutions out there that are very similar to the tool sets that are in MATLAB.
Great. Sid asks, why FuzzyLogic over using neural networks?
That's a great question. So one of the advantages of using FuzzyLogic is that you get a very quick and sometimes, let's say, rough and ready idea of what you're working with. Now, it may not always be possible to solve a complete system problem using FuzzyLogic, but if you're at the system identification stage and you just want an idea of what's happening, you just want to see, you're looking at perhaps one specific behavior of your system, of your device, FuzzyLogic is a great way to go about mapping that, visualizing what's happening. With neural networks and lower level system identification, that's when you can really drill down. I mentioned the training sets and the training iterations. That's when you quite often need to switch into one of those lower level approaches. So FuzzyLogic it's great because it is easy to use, it's easy to understand, it's based on really human vocabulary more than anything. So and as you saw from the example, just a few MATLAB commands allowed us to recover a signal from a lot of noise. So I guess you wouldn't necessarily use logic to solve a complete project, but it is a really great starting point, in my opinion. It's one of the things I do to get an idea of what's happening at a system level.
Great. Max Keen asks, are there any nonlinear systems that are being created that are novel, i.e. not emulating something analog?
That's a great question. The answer is yes. I'm working on one. I can't say any more than that. But you can really, there's a lot of creativity within DSP when you're not looking at an existing piece of hardware, when you don't have you're not constrained by rules and how people are going to perceive or A/B the original project against what you've done. So yes, other examples I'm trying to think of that have done that. There are a few very novel plugins that if a plugin house or a plugin developer mentions neural networks or AI or machine learning, then the chances are they've used some nonlinear mathematics, nonlinear approaches to create a new tool. I don't want to call out specific company names, but there's lots of really cool research and lots of great products. But look for those keywords. Look for things like neural networks, AI, and products that aren't referencing a vintage device, for example. But there is work being done, and as I say, I'm working on something. I wish I could tell you more. But yeah, be creative with nonlinear DSP, and don't use it just as a solution to a problem. Use it as a creative outlet as well.
Great. Joe Black asks, how do you deal with different sample rates in your training if your training happens in MATLAB?
Different sample rates. Well, it's a good question. Now, you really, with the FuzzyLogic example that I showed, because you're learning about the system as a whole, you're effectively you want to deal with your, well, the way I approach is I deal with my highest sampling rate first. So I want the highest resolution version, if you like, of what I'm looking to analyze. Manipulating sample rates themselves, that's really more of something that I would approach once I have my models, once I have my behavioral models, if you like, from the system identification that I've done, and that becomes more of an audio problem and less of a system identification problem, I guess is my answer there. So sample rates are really, I guess you could think of them as being a lower level in the process. So get your data set of whichever resolution you deem to be the best, however you're going to manipulate it, depending on how the resources you have to run through the training, computing power or whatever your approach is. And then once you have your reference models, that's when you would look at the things like sample rates and those kind of more audio stack related issues. I think that's what you're asking. I hope that makes sense.
Great. Sorry, that's my dog itching. Wait for her to stop. Okay. Joe also asks, what's your opinion on machine learning versus circuit-based physical modeling for nonlinear processing?
Awesome question. That's an awesome question. I don't want to be diplomatic about it. I actually think they go hand in hand. Now, have I modeled systems where I haven't had schematics available? Yes, I have. And I think there's a tendency when you have schematics in front of you and you start looking at nonlinear behavior on a component basis. So let's say you're looking at a Carnhill transformer from a mic pre. And you spend all of your time modeling that one specific component and before moving on to the next stage of the circuit design. I think there's a tendency to kind of get lost in the really, really low level design of a product. And that's when I suggest when I mentioned taking a step back. So quite often you really want to concentrate on what you actually want to get out of that model. And quite often it's, I prefer not seeing the schematics to some extent, because I can take a step back and really listen to and learn about the project and capture the characteristics without getting bogged down or tied up at a schematic level. And that's not always possible. And of course, there are instances where you need to look at individual components. But I would say with the advances in toolboxes that are in MATLAB and the advances in just AI machine learning methodology across the board, I think learning about systems, identifying systems outside of the schematic realm is becoming more and more doable, more and more accessible to those who might not have the analog electronics knowledge prior to taking on a project like this. So that's an awesome question. They both have their merits, but I think, I'm going to say it, I don't think you necessarily have to have a schematic before you approach the problem.
Great. We have another question from Sid. Can you share more about your approach for choosing appropriate stimuli for system identification?
Good question. So that really comes down to the type of project that I'm working with. So if I have let's say an IC-based EQ, which isn't designed necessarily to take a really driven signal, then I'm going to choose an input signal, input stimulus, which is appropriate and relative to that device. If I'm working with a mic pre, for example, then I'm going to want to find out how people are using it. And this goes back to when I was saying that you want to talk to people who've used that particular device, the expert users. Find out how they're using it. Find out if they're using it off spec, I like to say. So a lot of great sounds throughout history of recorded music have come from people experimenting and driving things harder than they were designed to be driven. So base your stimuli on that. As far as actual stimuli signals, I use a whole range. So everything from white noise to, sine waves, impulses. It really depends on the section of that device or the area of characteristics on that device that you're concentrating on. That's what type of signal you use. And of course, ultimately, you're going to be using real world signals. So actual recorded audio, driven audio, that kind of stuff. So use a combination of input stimuli when making models, when identifying systems. Don't tie yourself to one particular way of approaching it. Don't use white noise for everything, pink noise for everything. Use change the entropy of your input signal, because a lot of the times, if you have kind of time varying noise gates that you have with Rupert Neve devices, for example, hysteresis, then you want to vary the entropy of your input signal, of your input stimulus, because you want to be able to see how that entropy is, of course, another variable that exhibits nonlinearity in a lot of these devices. So, so choose your input signals carefully and kind of match them to what you're trying to understand from that particular device or that particular stage of the device.